Welcome back to Decaf-Math, and welcome if you are new here. Today, let's take a look at the law of sines. Law of sines. This was a requested topic, so thank you to the person who suggested this. Today, let's actually take a look at what the rule says and kind of set up a typical picture. And then let's take a look at sort of building the intuition behind why it works. And then in another video, we can do some specific practice problems that apply the law of sines. So we can dig out a scientific calculator and plug in some numbers, okay? But today I wanted to focus more on the big picture. Now, of course, don't worry if you've never learned this stuff, or you learned it a very long time ago and you can't remember anything. Don't worry, Decaf-Math here is just a space to relax, maybe review, maybe fall asleep, maybe catch some tingles along the way. So don't let the actual math overwhelm you or stress you out. There are plenty of opportunities for that to happen. So anyways, if you are learning this, I hope that this is helpful. So the law of sines, let's start out with what it says. So you'll either see it like this, typically, of course, or the other way around with everything flipped. Sine A over little a equals sine B over little b equals sine C over little c. And that's it. So for those of you who say that you don't make it to the end of my videos because you are so relaxed, so relaxed, this is the one takeaway. Okay? So notice that A over sine A equals B over sine B equals C over sine C. These two are actually the same, because if these are equal, I can do 1 divided by this equals 1 divided by this, which equals 1 divided by this. And when you divide by fractions, it's the same as multiplying by a reciprocal, by the reciprocal, meaning you flip the top and the bottom. And then you get 1 times the reciprocal, which is just them all flipped. So just algebraically, these two statements are equivalent. So you only really need to memorize one. So just pick your favorite. I typically prefer the top one, but we will give both of them love today. Okay, so we'll just kind of keep this in mind. But of course, what does it really mean? What are A, B, and C? And the setup actually makes all the difference for applying this. So let's draw out the picture. So first thing to notice is our trig function sine. Sine takes in an angle. So we already know just from this, A, B, and C, capital A, B, and C are angles. And the sine function and our trig function take in an input of an angle and give us a number. And that number actually represents a ratio. For sine, it's the opposite over hypotenuse, and we'll go over this for a right triangle. But that's why trig functions exist. We study them in trigonometry, which have to do with triangles. And our trig functions give us a way to relate angles, so measures of angles, with sides, which is really cool. So, in this case, we know that we have A, B, and C as angles. So I'm going to go ahead and draw a triangle. Just any triangle. And does this ever happen to you all? Every time I try to draw a random triangle, it somehow ends up looking right. I just have this tendency to go to right triangles. Maybe I just like being right, but I will make it a point to not make it right today, since that's just a special case of our law, and I want to show you how neat this is for any triangle. So that's pretty good. None of these angles are right. And also, for our random triangle, it doesn't matter if all the sides are equal in length, meaning it's an equilateral triangle. Very good. Or if two of the sides have the same length, meaning it's an isosceles triangle. Or if all the lengths are different, meaning it is scalene, yes. It does not matter. And it also doesn't matter if there is an angle that is obtuse, meaning bigger than 90 degrees. Okay, so it doesn't matter if your triangle looks like that, or like, whoa, like that. But just because I want mine to be cute, all my angles are cute. So this is just a cute. But I'll show you what to do for the proof when it's obtuse too, okay? So this is just my random triangle. Now at this point, you can label these points, these vertices, which are these corners, right? For a triangle, you have 3 vertices and 3 sides. You can label them however you want. A, B, C, pick whatever you want. This could be C, this could be B, this could be A. And of course you can fill in, whatever letters you want or whatever symbols you want, as long as they are corresponding. Okay. So the important thing is the pattern going on here. You don't have to obsess about like the letters, okay? So you have a cat, sine cat. You have a little kitty, puppy over sine dog, and oh no, I dug myself in a hole here. Pony over sine horse. Okay, so they have to be paired together, but the actual lettering doesn't matter. But let's just stick with the standard ABC. So I can pick this one to be A, this one to be B, and this one to be C. Okay. But once I set that, then we now know what the angles are. So technically my angle A is this angle, which makes sense, right? It's the angle at that vertex. This is angle B, this is angle C. If we are really trying to be, snooty about it. Lack of a better word. In my opinion, snooty. But if we really want to be really formal about this, angle A is actually angle CAB. That's the typical notation, although you can just write angle A like that. Okay? But it really is CAB. So if you've taken geometry or you're taking geometry, you might know that when you write out the angle, you want this part, this middle letter, is really our angle, right? So angle CAB is my angle A. And then angle B is CBA or ABC, as long as the middle one is B. Okay. It's just that, so these are the same. It's just that if I write CAB instead of A like this, and then, CBA here, and then sine BCA, let's say, that's just going to look really messy, very complicated, and it would pretty much scare more people away from math, and we don't need that. Plenty of people are already scared and hate math, so let's just keep it as simple and lovely so that people can stay into math. Okay, so that's what we're gonna do. So we label our angle A, angle B, angle C. And now once we've set these angles, this is where we have to label lowercase a, lowercase b, and lowercase c. And this actually does matter. So side A, or side with length A, it's the side that is opposite to my angle, or opposite from, right? So here's my angle A, the side that is across from it, that is lowercase a. Okay, so we just pair them together. Across from B is lowercase b, like that. And across from C, like this, okay? And the same idea will apply for law of cosines as well. So once you do set your angles, be sure you know which one is which side, okay? Because when we do practice problems, you'll want to be clear with which side corresponds to which angle for whichever law we're using, okay? Okay, so that's our setup. And again, same thing applies for our obtuse and right. A right triangle is actually just a special case for this, but even for obtuse one, same thing with the angles. Okay, so that's it. So what this tells me is that the ratio between the length of this side, so this is side A, but this is going to have a length, so I can just use my ruler for that. So that is, roughly, I don't know, like, so 0 is there, 4.45. Can't be super accurate with this, but 4.45. And it doesn't matter what units you use, as long as you label the units. And typically, if you don't see any units and you just see like numbers like 4.45, that just implies that all 3 units will be the same. But just know that whatever number is there, it represents distance or length, okay? So you can use your own unit of measurement if you so please. But if you do mix them, mix units, like say you measure centimeters here and inches here, make sure that there's a way to convert so that they are all the same unit. And typically, if you have like a diagram like this, they will all be measured in the same, so that's okay. And our angles A, B, and C will be in degrees or radians, and you can convert between the two, and I will link a video for how to do that in the info box. But you can measure your angle using a protractor, and you just put your dot here and line up your 0 this way. So 0's here, so you read that, and that's about 55 degrees or so. And you can do the same here, but going this way, right? And so you can get those angles, like I said, this reads in degrees, but you can do this in degrees or radians. And what this tells us is the length of this side divided by sine of my angle. You can plug that into your calculator if it's not a special angle that we know, say 30 degrees or 45 degrees or something. If you do that divided by sine of this, it should be equal or approximately equal if you're doing this by hand to this divided by sine of this, which should be approximately equal to this side, the length of this side divided by sine of that angle, which is just so cute. It's so simple, but it's not necessarily obvious. So, we can kind of build some intuition besides just like physically measuring with a bunch of triangles. That's really cool. You can show yourself that that works, but we should probably try to prove it in general. So that's what we're gonna do now. So the first thing that I have to remember is that sine is opposite over hypotenuse, and that's thanks to our wonderful little acronym SOHCAHTOA. And we're just going to use the SO part today. So sine of an angle specifically. This is for cosine and tangent. But sine of our angle is the side opposite over hypotenuse. But the question is here, what is the hypotenuse? What is the hypotenuse? So that is kind of a trick question. There is no hypotenuse in this case. And that's because this is not a right triangle. So hypotenuses only exist when we have a right triangle, and it is the longest side of a right triangle. But when we don't have a right triangle, it is not just the side with the longest length. Okay, so it's not C, or I think C is the longest here, but it's not just C. We have to have a right triangle to apply SOHCAHTOA in the first place. So I don't see one here. I don't see a right triangle. So I am just going to make one. Right. Mark your own path. So there's nothing right here, but I do have this side AB, and I have this thing right there. So I'm going to draw a vertical line down. Just going to, and by vertical I mean perpendicular, so right to this AB. So maybe like this. Ta-da! Right? So that this is right and this is right. So if I used my protractor, I should see that it is 90 degrees. Pretty good, right? 90 degrees this way and 90 degrees this way. So I'm going to label the length of that X. It's an auxiliary, right? Auxiliary line. So I made that. And now notice that I have two right triangles. So at first there was no right triangles. And then I had another little perspective, and now I suddenly have two. Isn't that nice? I have this and this kind of overlaps at my X, right? So just with one line, I made two right triangles. Now, if I look at sine A, so this angle, sine A, I can use this chartreuse. I love that color, and I like that word, so I picked it, chartreuse. But if I look at this chartreuse triangle right here, that's a right triangle, and I can see that the hypotenuse, which is the length of the side across from my right angle, is B, and this part is X, and I actually don't know what this is. I know that the whole thing is C, A, B, C, but this part I don't actually know. I could use the Pythagorean Theorem now that I know B and X. So this squared plus X squared should equal to B squared. So therefore, just using some algebra, the length of this is the square root of B squared minus X squared. But because I'm doing sine A, I don't actually care. I don't actually need that. So sine A is the opposite, so the length of the side opposite of my A, which is X, over the hypotenuse, which is B. Ta-da! That's it. So I'm going to start with that equation, and that just comes from my chartreuse triangle. And now let's take a look at my violet de Parme. Why did I violet de Parme? I picked some interesting colors, but fancy sounding. But this triangle, let's take a look at this triangle right here. So the hypotenuse is A in this case, and the side that's opposite is still X, right? So this is still X. Again, we don't know what the length of this little piece is for our violet triangle. We don't know what the length of that side is, but we don't need it. And I just noticed that there's a C written there, and I don't want that to be confusing. C is the length of the entire side, right? The entire side. So we don't know what this little piece is. But we do know that sine of B, of this angle B, is the length opposite, length of the side opposite, which is this X over A, where A is the hypotenuse for this one. So we have that. And so we have two equations just from the two right triangles that we got by breaking down our original triangle into two right triangles. Okay, good. So now we're going to do a little bit of algebra where we realize that this X is the same X for both triangles. So this X should equal this X. So what I'm going to do is from this first equation here, I'm going to solve for X. And all I need to do is move this B here on the bottom over to the other side, right? Or you can think of that as multiplying by B on both sides to cancel that out, right? So that this is B over 1, you just cancel it out. In either case, you can kind of think of that as moving the B over. So we get B times sine A equals X. See that? I'm just gonna pop that over there. And then from the other equation here, we can pop this A over to the other side. So A sine B equals X. And we know that these two two x's are equal to each other. Because we didn't do anything to it, it's still the same x. So we have b sine A equals A sine B. Yay. So cute, right? So from here, depending on which version you want to prove first, you just move either sine A over, or you can move the little a over here and the b over here. It's just algebra. And so I'm going to give the second version a little love. So I'm going to do this version, which means basically I'm going to move this little a over to this side and this little b over to this side. And when I say move, it's just the one-step algebra, right? So I have basically everything is multiplied. So this is a times sine b, b times sine a. And remember, just sine, that's a shortcut. Sine just alone doesn't mean anything. You always have to have sine something. So sine a, right? So that's one, sort of one unit. Sine b is 1 unit. So you're basically doing a times that unit and b times that unit. So when I move this over, I divide. So I'm dividing both sides by a, and I'm going to divide both sides by b. And if you want to do that in one big step, you can just divide by ab. Whichever. Either way, you get sine a over a, and then sine b over b, which looks a lot like this. So nice, right? So we have this first part, and if we want to include the sine c over c, you can do the exact same reasoning, flip this over, and do the same thing on the same triangle. You just draw a different height, or a different, you can call that y, something else that's perpendicular. And now do the same logic with the c and maybe b, or you could do it here with c and a. You only need to do it one more time, just whichever one you choose, because you can get the same sort of ratio for sine a over a equals sine c over c. And since we already proved that this is true, and then if this equals to sine c over c, then just by the transitive property, they're all equal to each other, right? So, or if you do the sine b over b equals sine c over c, then they're still all equal, just because we already did this one. Nice. So that is it. That's the intuition for how to prove this. And like we said, these two are algebraically equivalent. So if you can prove this, then you can just do the 1 divided to get this version of it. So I hope that this is interesting. I will point out that if you want to do the same proof, but for an obtuse triangle, it's the same logic. So that's really ugly, but if you have like an obtuse angle, you might end up with a height if you try to draw perpendicular to make a right triangle for SoHCAHTOA. Again, you will get a height that is outside of your triangle, and that's totally okay. You just follow along with your SoHCAHTOA, or just the so, but the opposite over hypotenuse. But you might also need to include the fact that you might have like a 180 minus an angle at some point, and you might need the fact that sine of, let's say, an angle theta is the same as sine of 180 degrees, or just pi radians, minus theta, for theta between 0 and 180 degrees. And the reason for that is that for your unit circle, because remember our sine and cosine is very strongly related to our unit circle. Sine of our angle is actually the y coordinate, and when we draw this angle, the sine, this y coordinate right here, is the same as the y coordinate here, but it's also the same as this 180 because the whole thing here is 180. I don't know if you can see this, but if this is 180 degrees, which is half of our entire circle, the y's are both positive here and here, which the angle would be here or all the way there. So it's through symmetry that you know that the two sine parts are the same, okay? Because the y coordinates are both positive. So it's basically reflecting a right triangle across the y-axis over here. So you have this property, and you know that theta is going to be between 0 and 180, not inclusive because we are talking about triangles. And for triangles, the sum of the interior angles must equal 180 degrees. So of course, an angle can't be 0 degrees because we wouldn't have a triangle. That would just kind of disappear, and we'd basically have a line. And similarly, if one of the angles is 180 degrees, but the sum of the interior angles have to be 180 degrees, you basically force the other two to be 0. Because we can't have negative interior angles like that, right? So we can't have like negative 2 degrees and positive 2 to cancel to be 0. So you can't have an angle be 180, you can't have an angle be 0. So, and everything else is going to be in between, right? So you can use this fact for your obtuse triangle case if just for whatever reason you were interested and wanted to try the proof with an obtuse case, okay? But actually along that line, when you start practicing some of these problems, basically it'll look something like, I'll give you A and B, maybe lengths of two sides and one of the angles, and you can tell me what the value or the measure of the other angle is. It might be to say fill in the entire triangle, meaning fill in all missing lengths of sides and angles, in which case you might need to use the fact that, you know, once you find two of the angles, that the sum of the three will be 180 degrees. And then from there you use the law of sines again to get the third length. You might have it the other way, where you are given angles and one side, and you need to calculate the length of the other side. I'm not sure if that's what I just said, but basically you will have three. Basically, if you have just like one of these, just these two parts, you'll have 3 of the 4 so that you can calculate the other. And then from there you can calculate the C part as well. But those are typically what you need to do, is fill in the whole triangle, or just fill in the length of one side, or find another angle. But you should be given 3 of the 4 pieces, or enough pieces for you to be able to figure it out using what you already know. Okay, so we will do some practice with this, but if you happen to be working on this right now and you seem to be like getting most of the questions okay, you're doing the algebra okay, which typically if you're stuck and you're getting something wrong a lot, it might mean that you're moving things around a little bit off, like the algebra part. So sometimes people get things wrong and they're like, what, I don't understand math at all. But maybe you understand law of sines okay, but maybe it's the algebra that's throwing you off a little bit. So be patient with yourself, it's all okay. The only other thing I wanted to mention really quickly is there is one particular situation where you might need to find like a measure of angle B, and you have, let's say, A and B, and you have sine A, or you have A and you can find sine A, and let's say you cross multiply, divide by A, whatever, and you get that sine B equals let's just make up something like 2.348 or something. Okay, so I will mention this again when we practice the problem, but if we do this and we say, okay, well, B equals sine inverse of 0.2348, and you just type this into your calculator, you get one answer. That'll give you some, depending on if you're in degrees or radian mode, you will get some answer, right? And if in your picture you know that B is an acute angle, meaning less than 90, then you can go ahead and just put in whatever this answer is. However, if it's an open-ended question and you don't know what the shape of the triangle looks like, it's actually possible to get two values. So this is just kind of like a heads up. There's a particular situation, and it's involved when you need to find an angle. So going from lengths of sides and one angle to finding another angle. And if you know nothing about that angle B, but you say, well, what can be B? What can the measure of angle B be? It's possible to get two answers. And the reason is actually exactly this. It's exactly from this unit circle situation, because when it's positive, you have two answers. So you could get the answer that your calculator tells you, but it's also going to be missing the situation where you do 180 degrees minus whatever it is that you get. Or if you're in radians mode, just pi minus whatever it is that you get. Okay, so that's more of like the open-ended question, but that's one particular scenario, but it's so commonly confused, but that I wanted to just throw it in there here for now so that we can repeat it again in the future. Okay, but that is really it just comes from a good understanding of how the sine function works. But as usual, whenever you work with like inverse of any trig function, it's good to think about what period you are on, right? Like, is there ever going to be another situation in your domain that would still make our situation true and work, right? So within our scope, is there some other value that could also apply? And so sometimes you will get two answers. But anyways, do this as you normally would. We will apply some algebra here. Once we apply, fill in what we know, and we will do some practice problems soon. Anyways, I hope that you found this interesting, relaxing, and whether or not you are learning this stuff or you learned this stuff long ago, either way, I hope that you are resting very well, and